Hello, now we will talk about polytropic process relations. So for a polytropic process we have the following relationship: PV to power n is equal constant. So as we said before, that depending on the value of n we can know the nature of the process. So let's say for n is equal to 0, we can say that the process is isobaric. So isobaric, that means that P is equal to a constant. For n is equal to infinity, the process is isochoric or isometric. That means that in this process V is equal to constant. For n equal to 1, this will be isothermal process, and T in this case is equal to constant. So for n is equal to 1, we will have PV equal constant, and as we know, for an ideal gas, PV is equal to mRT, and since in a closed system the mass is constant, so if mRT is constant, then the temperature should be constant, and in this way we will have an isothermal process. So this polytropic process relation applies to any gas. So if we apply it to a gas, and for an ideal gas, we have PV equal to mRT, we can obtain further relationships. So what we are trying to do here is to obtain a relationship that relates the temperature variation to the volume variation, and the temperature variation to the pressure variation. So since temperature is really important in the calculation of an ideal gas, since we said that the internal energy for an ideal gas depends on the temperature only, and the enthalpy for an ideal gas also depends on the temperature. So we want to relate the temperature to the pressure and the temperature to the volume. So if the pressure varies, we can know the temperature, how the temperature will vary, and if the volume varies in a polytropic process, how the temperature will also vary. So the ideal gas law, let's say we apply these equations between two states, 1 and 2. So let's say an ideal gas is undergoing a process between two states, 1 and 2. So we can always say at any state we can apply the ideal gas law: P2V2 equal mRT2, and P1V1 is equal to mRT1. Also we can say that P2V2 to power n is equal to P1V1 to power n, and is equal to the constant. So let's divide these two equations. So we will obtain T2 over T1. The m and the r will cancel out. Since this is a closed system, the mass is constant and the r is constant for a given gas. So we will obtain P2 over P1 into V2 over V1. So let's try to determine an equation T2 over T1 function of pressure only. So we need to replace V2 over V1 by an expression for pressure. So we will use the following relationship here. So we will have V2 over V1 to power n will be equal to P1 over P2. So V2 over V1 will be equal to P1 over P2 to power 1 over n. So if we replace this equation here, then we will have T2 over T1 is equal to P2 over P1 times P1 over P2 to power 1 over n. We can write it as P2 over P1 to power minus 1 over n. So in this way we will obtain that T2 over T1 will be equal to P2 over P1 to power n minus 1 over n. So this equation, we can use this equation to determine the temperature given the pressure at the end state. So if we know the pressure at the end state, of course we should know the initial conditions T1 and P1, and if we know the pressure at the end state, using this equation we can know the temperature, and if we know the temperature, then we can calculate the internal energy and the enthalpy using the tables or using the specific heat data. So this is the first equation, relates the temperature with respect to the pressure variation. Now we will derive an equation that relates the temperature to the volume variation. So in this equation we will replace P2 over P1 by an expression for volume. So as we said, that P2 V2 to power n is equal to P1 V1 to power n. So P2 over P1 is equal to V1 over V2 to power n. So in this case, T2 over T1 is equal to V1 over V2 to power n. So we replace this term here in this equation into V2 over V1, so we can write it into V1 over V2 to power minus 1. So in this case we will obtain T2 over T1 is equal to V1 over V2 to power n minus 1. So this equation is important. If we know the volume at the end state, we can know the temperature at the end state. Okay. So let's see that we want to calculate the work for an ideal gas undergoing a polytropic process from 1 to 2. So it is integral from V1 to V2 of PdV. And since PV to power n is constant, we can replace the pressure by the constant over V to power n. So the work from 1 to 2 will be equal to the constant integral V1 over V2 dV over V to power n. So P is the constant over V to power n. So we will have the constant in the integral will be equal to V minus n plus 1 over minus n plus 1 or 1 minus n from V1 to V2. So we will have a constant into V2 to power 1 minus n minus V1 to power 1 minus n over 1 minus n. So the constant here can be, so the constant can be either P2 V2 to power n or P1 V1 to power n. So when doing the multiplication, if we want to multiply by the first term V2, we can use the constant as P2 V2 to power n. And when we multiply by V1, the constant is P1 V1 to power n. So this will simplify the equation. So we will have P2 V2 to power n into V2 to power 1 minus n minus P1 V1 to power n into V1 to power 1 minus n over 1 minus n. So in this way we will have P2 V2 minus P1 V1 over 1 minus n. So for an ideal gas, P2 V2 is mRT2 and P1 V1 is mRT1. So the work from 1 to 2 will be equal mR T2 over T1 over 1 minus n. So if we want to write it per the specific work, or we can say small w, it will be equal to R T2 minus T1 over 1 minus n. So this equation is applicable, of course, if n is not equal to 1. So for none, if the process is not isothermal. However, since here we will have a division by 0, so let's say if n is equal to 1, we can just go back to the integral PdV V1 to V2, and we have PV to power 1 is equal to constant, so PV equal constant, and we replace the pressure by the constant over V, so the work will be equal to the constant integral dV over V from V1 to V2, and the constant can be either P1 V1 or P2 V2, and integral dV over V is just ln V2 over V1, and in terms of temperature we can write W from 1 to 2, excuse me, this is P1 V1. So P1 V1 is mRT1 ln V2 over V1. So in the specific work, small w is equal to RT1 ln V2 over V1. Of course, this equation is valid if n is equal to 1. So we can use the following two equations to calculate the work for an ideal gas undergoing a polytropic process, and also we can use, if we want to know the temperature of the gas undergoing a polytropic process, from given values of pressure and final volume, we can know the end state temperature in order to help us calculating the internal energy and the enthalpy.